Welcome to topology sessions. Last class we have discussed about some of the examples of topological spaces. Today also we will discuss one theorem and some examples of topological spaces. The last class we have stopped by co-countable topology, a topology in which the open sets are co-countable. That is, its complement is going to be uh, countable, means we will say that it's a co-countable topology. Today we are going to see a theorem. Let X be a set. Let X be a set and tau I set or Ti, comma I belongs to I. It's the indexed set, right? Be a indexed family of be a indexed family of topologies on X. Let tau is or T is equal to intersection I belongs to I, Ti, then T is a topology on X. That is, whenever you are having a set and a collection of topologies on that set, then their intersection is also a topology on X. And it is weaker than is weaker than each Ti, comma I belongs to I. And second one, if U is any topology on X, any topology on X which is weaker than each, which is weaker than each Ti, then our T, that is the intersection, is stronger than U. So we want to prove whenever a set is given and a collection of topologies on the set, that intersection of the topologies will form a topology. So proof, tau is a topology on X or T is a topology. So we have to prove tau is a or T is a topology on X. Now each tau I is a topology, since topology first condition is empty set and the entire set belongs to Ti for each I belongs to I, which implies empty set and entire set belongs to or the intersection I belongs to I of Ti. Now this is nothing but T. So for empty set and entire set belongs to the intersection, that is the T. Next we show that T is closed under finite intersection. Finite intersection. Let A1, A2, extra some AN belongs to T. And suppose their intersection A is equal to intersection J equal to 1 to N AJ. Now we have to show that this A belongs to top. Now we have to show that A belongs to T. Since T equal to intersection I belongs to I of Ti's, comma, each AI or AJ belongs to I. Because this belongs to top or T, that means each AJ belongs to uh, T, Tj, right? Tj or J belongs to I can take, which implies their intersection, right? Which implies intersection AJ, J belongs to I, sorry, J equal to 1 to N, right? So J equal to, made a mistake here, not J belongs to I, J equal to 1 to extra up to N, then this equal to J equal to 1 to N, AJ. This belongs to intersection I belongs to I of Ti. What's the reason? Since each Ti is a topology, since each Ti is a topology which should be closed under finite intersection. Therefore, what you are having is these intersections belongs to Ti or Ti. So we can have no intersection here. This belongs to Ti. That's better. This belongs to Ti, which implies this intersection AJ belongs to top because it belongs to each of them, so it belongs to the intersection. Now similarly we can prove that T is closed under arbitrary union. Closed under arbitrary union. Now we want to prove few more facts, that is this is going to be the smallest topology. See, it is the weaker than each top I or each Ti, And if U is any topology on X which is weaker than each Ti, then T is stronger than U. This all follows from the intersection properties, because T means intersection of all such Ti's. So definitely this T should be contained in each Ti, right? So T is weaker than each Ti. Now similarly, if U is any topology on X which is weaker than each Ti, then this U is also contained in this T, right? So T is stronger than U. So remaining, we can conclude by stating in this fashion, which is the property of intersection. So remaining follows from intersection property. Intersection property. Next is a corollary. Corollary. Let X be a set, and D a family of subsets of X, a family of subsets of X, then there exists a unique topology T on X such that it is the smallest topology. It is the smallest topology on X containing D. So this corollary means if X is a set and D a family of subset of X, then there exists a unique topology tau on X such that which is going to be the smallest topology on X containing D. So proof technique is very easy. We are having a topological space X and it has got a subset D. You go for those topologies which contain D. So you may have lots of topologies which may contain your D. So one topology is something like this. I have got. Now another topology will be this is another one which is containing D. Go for another two. So this one is another topology which is containing D. So we consider all such topologies which containing D. Now take the intersection of all these topologies. Definitely that will result a topology by our previous theorem. Okay, now this topology should be the smallest topology on X containing D, since we are taking the intersection. Proof. Consider the collection of all topologies, the collection of all topologies on X which contain D. which contain D. This family is non-empty. What's the reason? Because you can have the power set topology that definitely contain D, which contain D. This family is non-empty since the discrete topology and the name is power set topology surely contain D. Now let T be the intersection of be the intersection of the members of of this collection applying theorem above tau is a topology or T is a topology on X. It contains D. For each topology will be a member of collection. For each such topology will be a member of the collection of topologies of the collection of topologies just considered just considered and hence stronger than its intersection and the uniqueness of T is trivial since we are taking the intersection. So we have defined a topology which containing D which is weaker than any of the topologies Ti. Now this topology is called the topology generated by the family D. So as a note we can write it down. Note, the topology so obtained is said to be generated by the family D. generated by the family D. Now we are going to the fifth example of topological spaces, the usual topology on R. The usual topology on set of real numbers. Usual topology on set of real numbers, which is defined as the topology induced by the Euclidean metric. Is defined as is defined as the topology induced by the Euclidean metric. Induced by the Euclidean metric. So what is the Euclidean metric? Yes, you know, by distance formula and all, you will be very familiar with this metric. Note that with respect to this metric, the open balls are nothing but will be bounded open intervals. So note that with this metric, the open balls are just bounded open intervals. Just bounded open intervals. So all bounded intervals are all bounded open intervals are indeed open sets in the usual topology on R. Since all bounded open intervals since all unbounded open intervals can be expressed as union of bounded open intervals. They are also open in usual topology. That is what it means is R with usual topology. Meaning is R with usual topology. So as before, you are writing this as R top or RT. In this case, your T is defined as set of all A comma B such that A comma B belongs to R. So this is your topology here. So in order to define this interval, we are making use of metric, right? That is the usual metric. So it is called Euclidean metric induced topology. And the last statement, that is the unbounded intervals. Suppose you have got an unbounded interval minus infinity, infinity. This can be represented as union n belongs to n of minus n comma n, right? So this is the bounded one. Okay, so we are expressing this as a union of bounded intervals. So this is the whole meaning of whatever you have written here. So real number with this topology is said to be the usual topology. Next we are having one more topology on R, that's called semi-open interval topology. Interval is called semi-open interval topology. Or you have open interval. So when you consider this semi-open intervals here, we'll get another topology. So sixth example is semi-open interval topology. Semi-open interval topology. Semi-interval open topology. A subset U is said to be open in this topology if for every x belongs to U there exists some r greater than 0 such that the semi-open interval x comma x plus r is contained in U. That is, if a subset U is said to be open in this topology, if for every x belongs to U, there exists a r greater than 0. The semi-open interval closed x, open x plus r is contained in U, and that the topology and the topology so defined is stronger than the usual topology, stronger than the usual topology, since You're having the reason since x comma x plus r when you are considering, this definitely belongs to closed x comma x plus r. So always your is stronger than the semi-open interval topology is stronger than the usual topology. Now the sequence. Now the sequence xn converges to y, converges to y in the semi-open interval topology, in the semi-open interval topology, if and only if it converges to y, it converges to y from above, from above, or from the right in the usual topology. The usual topology. See, real number with usual topology, we haven't discussed the convergence of sequence there. That is because you have studied that as an entire topic in your real analysis class. Now, in semi-open interval topology, the sequences will be converges. This of the form some x comma x plus r, no? So from this side, it's convergence. That is converges to y from above or from right. So from right, it is converges in the usual topology means we will say that the sequence converges in the semi-open interval topology. So today we have discussed about one theorem, that is if X is a set and a collection of topological spaces are given, then their intersection is also a topology. And we have come across an important corollary, that is the topology generated by a subset. Okay, for getting that, what we have to consider is we should consider all the topologies which contain D and take its intersection. And we have seen two more examples, that is the usual topology on R and the semi-open interval topology on R, and their comparison too. Their comparison is topology so defined, that is semi-open interval topology is stronger than the usual topology. So with this, I am winding up today's session here. Thank you for your patient listening. Thank you.